One single battery order just broke every record the energy industry has ever seen. 60 gigawatt hours signed in a single deal. To put that number into perspective, it's enough stored energy to charge every smartphone on planet Earth, all at the exact same moment. Not most of them, all of them. And this wasn't some startup chasing hype. It was the largest battery manufacturer on the planet, placing a bet on a chemistry that most experts had written off as unrealistic just 2 years earlier. So what exactly are they building? And why would the biggest player in the industry stake this much on it? Here's the part that sounds almost like a joke. The material sitting at the core of this battery isn't some rare earth metal mined from a war zone. It's cheap, it's boring, and it's sitting in your kitchen cabinet right now. Sodium. The same element in ordinary table salt. A battery built from something this ordinary just became one of the most disruptive stories in global energy. And that raises an obvious question. If salt is really this powerful, why did it take the industry 30 years to notice? The answer starts with the technology sodium is now trying to dethrone. 3 men spent decades solving one puzzle before anyone called it lithium-ion. Stanley Whittingham proved the core chemistry could work back in the 1970s, funded by Exxon during the height of the oil crisis. John Goodenough spent the next decade reworking the cathode until the voltage nearly doubled. Akira Yoshino spent the 1980s making the whole cell stable enough that it wouldn't destroy itself after a handful of charges. The Nobel Committee finally caught up with what they'd built in 2019, 34 years after Yoshino's own breakthrough. Sony built the first commercial cell around that science in 1991, tucked inside a camcorder battery pack. Within a decade, the same chemistry had spread into laptops, then phones, then almost anything with a plug. Physically, lithium had an advantage that felt almost unfair to compete against. Its ions rank among the smallest and lightest of any element used in a battery, so engineers can pack an enormous number of them into barely any space at all. Pair that density with lithium's strong pull to send electricity through a circuit, and you get the entire reason a smartphone fits in your pocket instead of your backpack. The growth curve that followed is hard to overstate. Global production has climbed roughly 27 million-fold since that first camcorder cell. Prices, meanwhile, have fallen 99% across 3 decades. Few technologies in industrial history have scaled that fast, or that far. Every one of those production doublings paid for something more valuable than a cheaper cell: confidence. Airlines certify it to fly by the ton. Automakers build 2,000-kilogram vehicles around it without a second thought. That kind of certainty doesn't come from a marketing department. It comes from 3 decades of the same chemistry behaving exactly the way engineers expect, shipment after shipment. None of that explains why a fully charged pack can occasionally catch fire in a parked car, or why the same battery that performs flawlessly in Arizona can lose nearly half its range on a freezing morning in Oslo. Those aren't flaws Sony could have caught back in 1991. They're baked into the chemistry itself. Lithium doesn't fail quietly. When it fails, it shows up on fire department reports, on winter range charts that crater overnight, and on repair bills that run 5 figures deep. A punctured cell, an overcharge, a moment of overheating, and the electrolyte inside doesn't just fail. It ignites, then floods heat into every cell packed beside it, and an entire pack goes up within seconds. Samsung found this out in 2016. The Galaxy Note 7 vanished from shelves on every continent after a wave of battery fires. That was a phone. Scale the same chemistry up to power a 2-ton vehicle, and the stakes stop being about a recall. They become about survival. More than 800 fires, 30 lives lost. In New York City alone, since 2022. Hold does something even more insidious. Below freezing, lithium ions can't slot into the electrode fast enough, so raw metal plates onto the surface instead, a process engineers call lithium plating. Those deposits grow into microscopic spikes called dendrites, and dendrites are exactly what shorts a cell from the inside. Even short of that failure, the range hit alone is brutal. 20 to 40% gone in a single winter morning. In Norway, in northern China, that's over 100 kilometers erased before breakfast. Then there's the bill nobody wants to open. A full pack replacement lands squarely in 5-figure territory, $5,000 on the low end, $20,000 or more on the high end. None of this makes lithium a flawed technology. It makes lithium a technology running into the limits of its own physics limits that eventually pushed researchers back toward an element they'd abandoned decades earlier. Ford Motor Company took a serious swing at this in 1966. Their sodium-sulfur cell, built by researchers Neil Weber and Joe Coomer, roughly doubled the energy density lithium would later achieve, but only at operating temperatures above 300 degrees Celsius, hot enough to liquefy lead. Nobody was putting that under a family car's hood. The deeper problem sat at the atomic level. Picture graphite as a parking garage built for motorcycles level after level, spaced just far enough apart for a lithium-ion to glide straight through. A sodium-ion is closer to a delivery truck. It doesn't fit between the levels, and forcing it in cracks the whole structure within a handful of charge cycles. On ordinary graphite, sodium barely gets stored at all, roughly a tenth of what lithium manages in that exact same material. For 4 decades, that single mismatch buried sodium as a serious contender. Papers kept publishing. Almost none of them moved the needle. Then, in the year 2000, 2 researchers in Canada found the opposite of what everyone assumed the answer would look like. Every battery breakthrough before this one had chased more order. Cleaner crystals, tighter stacking, more perfect geometry. This one went the other way entirely. They built a carbon structure engineered to be messy, structured anarchy at the atomic scale, riddled with disordered pockets. And inside that chaos, a sodium ion finally had somewhere to sit without breaking anything. Reversible capacity leapt to nearly match lithium's own performance on graphite. They called it hard carbon, a material that only worked because it refused to be orderly. But hard carbon had a flaw hiding inside its own chaos. Those same disordered pockets that made room for sodium also made the material porous. And porous means thirsty. It drank in moisture like a sponge, and a single trace of water inside a working cell was enough to poison it slowly from within. For the next 25 years, that invisible enemy stood between hard carbon and anything resembling a real product. Engineers had found the fix. Now, they just had to survive the thing that kept destroying it. The company that finally beat that enemy wasn't a startup chasing a moonshot. It was CATL, the same manufacturer behind the record-breaking order from the start of this video. In April 2025, they gave their sodium chemistry a name, Naxtra. By December, it was rolling off production lines, not laboratory benches. Water was the first law of physics. CATL had to bend. They coated every single particle so it pushed moisture away instead of soaking it up, and locked humidity on the production line down to levels most factories never even bother measuring. The sponge that used to drink itself to death stopped drinking altogether. Raw, hard carbon, under a microscope, looked like an unfired clay brick, porous, rough, prone to trapping gas inside its own pores every time the cell charged. CATL rebuilt it into something closer to glazed ceramic tile. Dense, smooth, sealed shut. Same chaotic structure sodium needs to survive inside. None of the gas-trapping mess that used to ruin it. Getting that material to stick permanently to the aluminum foil beneath it through non-stop expansion and contraction took an adhesive engineered at the molecular scale. And instead of building a separate anode at all, CATL let the sodium paint its own anode directly onto the foil during the very first charge, a coat so thin and so even it added back far more energy density than the trick had any right to deliver. The result closes a gap that looked unclosable 2 years ago. Energy density now sits close enough to standard LFP cells that most drivers would never spot the difference on a spec sheet. Cycle life pushes past 10,000 full charges before any real capacity loss in specialized deployments. That's the equivalent of driving to the moon and back 7 times without ever swapping the pack. Remember that freezing morning in Oslo, the one that could gut a lithium battery's range by half? This is where sodium turns around and hits back. At that same minus 30 degrees Celsius, Naxtra throws out almost 3 times the discharge power of a standard lithium pack. Drop the temperature to minus 40, and the cell still holds on to more than 90% of its capacity. Push it all the way to minus 50, colder than anywhere a production car has ever been driven, and it just keeps going. Charging matches that same defiance. A full pack reaches 80% in 15 minutes at room temperature, and even locked inside a deep freeze at minus 30, it climbs from nearly empty to 80% in half an hour. Engineers drove nails straight through it, crushed it under a mechanical press, cut into it with a hacksaw, overcharged it on purpose, hunting for a failure. Nothing. No fire, no smoke, no runaway reaction of any kind. This cell didn't just survive China's toughest battery safety gauntlet, it became the first sodium-ion battery in history to walk through it untouched, and every car built on a Naxtra pack from here on inherits that same immunity. This isn't sitting in a lab anymore. Right now, on ordinary Chinese streets, a budget-class sedan called the Changan Nevo A06 is doing something no lithium car has managed yet. Putting real drivers into a real commercial fleet, powered entirely by a battery that never touches lithium. It's the car quietly ending the idea that electric and affordable can't be the same word. CATL and NIO built the infrastructure to back that up, and it solves the exact pain from earlier in this video. In the cold regions where lithium owners used to sit through an hour-long charge just to get moving again, a Naxtra pack now gets swapped for a full one faster than most people fill a gas tank. Remember that record-breaking order from the very first seconds of this video, the one that could charge every phone on Earth at once? That was CATL signing a 3-year, 60 gigawatt-hour supply deal with the storage giant Hyperstrong, plus a separate 5 gigawatt-hour agreement that brought the same chemistry into the European grid. This isn't a lab curiosity chasing investment. It's already load-bearing infrastructure. Then there's the copper exorcism. Copper is the red gold of the clean energy transition fought over, price gouged, and mined from a handful of politically fragile places on Earth. Every lithium battery needs it. Naxtra needs zero. CATL ran aluminum straight through the entire cell instead, and that single decision alone erases roughly 70% of the current collector's cost, before sodium's own chemistry saves a single additional cent, which brings us to the number the entire industry has been chasing for a decade. Sub-$20 battery cells. CATL's own mass production target lands at $19 per kilowatt hour against $55 or more for standard lithium iron phosphate. That gap isn't a discount. It's the price point that makes a gasoline engine look like the more expensive option. $19 a kilowatt hour doesn't just undercut lithium. It's close enough to make the internal combustion engine's last remaining advantage, sticker price, disappear. Sodium can't do everything. Its ions are heavier and physically larger than lithium's, and that one fact puts a hard ceiling on how much energy the chemistry can ever pack into a given weight. For a family sedan doing errands around town, that ceiling barely matters. For an aircraft or a phone that has to survive a whole day in someone's pocket, it matters enormously. CATL's answer wasn't to pick a winner. It was to stop treating sodium and lithium as rivals and start treating them as two specialists sharing one job. Their dual power pack splits a single battery into two zones, one built from Naxtra cells, one from standard lithium chemistry, both wired into the same software brain. Start the car on a frozen morning, or plug in for a fast top-up, and the sodium zone takes the load, doing exactly what it does best. Push the car onto a highway for a 6-hour drive, where every extra kilometer of range counts, and the system quietly shifts the weight onto lithium instead. Neither chemistry is ever asked to do the job it's bad at. That single design decision is already rolling out across passenger cars, heavy trucks, charging stations, and grid-scale storage. Sodium didn't have to replace lithium to win. It just had to earn a permanent seat next to it. Here's the part CATL's marketing team won't put on a billboard. Naxtra has only existed at commercial scale since the end of 2025. Nobody has tracked this chemistry through 15 years of real driveways, real winters, and real degradation, the way engineers have tracked lithium since the 1990s. The safety tests are real. The decade of quiet, boring proof that lithium eventually earned? That clock only just started. Not every Chinese battery giant is placing the same bet, either. CATL is building a chemistry meant to go anywhere. Cars, trucks, grids. BYD walked straight past passenger vehicles and poured its resources into a completely different sodium chemistry, built purely for stationary grid storage. Their material, a polyanion structure called NFPP, had a problem that should have killed it outright. It conducted electricity almost like rubber, not like metal. BYD's fix was brutal precision, shrinking every particle down below 100 nanometers and wrapping each one in a shell of carbon, multiplying conductivity several times over. Their target, a price point low enough to build a monopoly fortress around grid storage before anyone else gets there. Two of the most powerful battery makers on Earth looked at the exact same element and placed two completely different bets on where it wins. That kind of disagreement, at that scale, is usually a sign the real fight hasn't even started yet. This is the number that actually rattled people outside China. A production cost near $19 per kilowatt hour doesn't just beat lithium on a spec sheet. It rewrites what a competitive EV supply chain is even allowed to cost on a timeline most Western manufacturers weren't planning for. America does have a sodium battery company of its own. Natron Energy builds a Prussian blue chemistry prized for extreme safety, already running inside data centers and grid installations that need power without the fire risk. But Natron isn't chasing passenger cars. It's staying in a lane where lithium's weaknesses matter least. France's Tiamat took a different narrow lane. Ultra-fast charging for handheld power tools, not vehicles. Both companies are building real useful technology. Neither one is trying to put a $20,000 sodium sedan into a driveway in Ohio or Lyon. China is the only place on Earth right now building sodium batteries for the one market that reshapes an entire industry. Everyday cars, at everyday prices, sold to everyday people. Whoever wins that race doesn't just sell batteries. They get to decide what the next decade of the global auto supply chain looks like, and right now, only one country is playing that game at scale. A battery built from something you'd shake onto dinner just forced the world's biggest lithium producers to rethink their next decade. It survived cold that stops lithium in its tracks. It undercut lithium on price using a metal most factories treat as scrap. And it did all of that in under 5 years. Starting from a chemistry the industry had already given up on twice. Lithium isn't finished. Cars still need range, and range still needs light, energy-dense cells that only lithium can deliver at scale. But for the first time in 30 years, lithium has company at the table, sitting in the exact seat everyone assumed only lithium could ever fill. So here's the question worth sitting with. When the cheaper battery and the safer battery turn out to be the same battery, how much longer does the more expensive one get to stay the default?